Hello, this is Sumnik. I did not expect that the round will be so early, so it's already running for almost 20 minutes. But let's start. I will participate in this round and explain what I'm doing. Problem A with subtasks. This is interesting. Alright, problem A. We have a string of letters A and B. We have to split it into 3 parts so that the second string is not strictly between the other two lexicographically. But like the limitations are so small, we can just try everything and compare in linear time. But what is this problem about? And in second problem, in second problem the strings are big, we cannot try everything. Okay, let's just try to solve the second one. So we want to make the middle string either the largest lexicographically or the smallest lexicographically. Can we somehow make sure that the middle string starts with letter B, but both of the other strings start with letter A? Well, for that, the first letter should be A, and we should have another A somewhere and some B between them. So if the string starts with A, then we have B somewhere, then we have A somewhere. We can like cut before this B, cut before A, and thus the middle string will start with B, but both of the other strings will start with A. Okay, and we don't actually need the second string to start with A, we just need it to be at most as big as the middle string, but that can be achieved just by saying that it will have the length 1. So it's either just A or just B, and both of them are not bigger than any string that starts with B. So if given string starts with A and it has B somewhere not in the last position, then we can do that, for example. But that's like a lot of ifs. should be simpler than that, right? Like right now we will have to like even if the string starts with A, we will have to consider two more cases when there are no B's or when the only B is the last one. Or we can try to make the middle string the smallest, and if we just make it to be string A, it's the smallest of all the strings except the empty one. So if we can make the middle string to be just A, we won. That is possible if there is A that is not first and not last. Okay, otherwise we will have like everything in the middle, like everything except the first and the last are B's. So let's just say that the first string will be just first letter, the last string will be just last letter, and the middle string will be all B's that are in the middle. Then it's surely not smaller than both of those strings of length 1. Yeah, that's simple enough. I guess it will be simpler with strings and C. So we are checking if all the middle letters are B. If they are, we will do something, and actually we will print first letter, then everything in between, and yeah, I should print spaces, and then the last letter. Otherwise I need to find this middle A, and then print everything before it, then this one letter, and then everything after. In problem B, have an array of n integers we want to check if there are two different subsequences for which the ORs are the same. But the numbers are given in some weird way, right? We are just given the 1 bits in binary representation. And we are only interested in yes, no. Don't have to actually restore the answer. Okay, well, if we can find some subsequence and then remove one of the elements so that OR doesn't change, the answer is yes. What does it mean? That means that the number we remove should should have ones only on positions that or of the other numbers in the set already have ones. Well, that means that it's always good to make this other set bigger, so we will actually take all of the numbers and try to remove one of them so that OR doesn't change. Now, how to check that? Well, we need look, we can calculate for each bit in how many numbers it appears as 1, and then if there is a number in which every set bit appears in at least one some other number, then the answer is yes. So we can just calculate all of that. Like we will have an array CNT for in which we count for each bit how many times it occurs, and then we just run through all of our numbers once again and check if for all the bits this number have CNT is at least 2. Like 1 coming from this number, and at least 1 should come from all the other numbers. The only issue I can see with that is that we should clear this array between multitests, and like if these things would be bounded by n, then we could just clean them in O of n. We know that like the sum of them is bounded by something small, but like they can be big. It is probably fine to use some fast way of zeroing the array out, like memset. But the other thing we can do is we can clear only the elements that we have changed from 0. So we will read everything, calculate CNT, find the answer, and then again run through all of the bits we have and zero their CNT out. That's not what I wanted to do. So I have read all the bits, and for each bit did ++ in CNT. Now we will try to find the number for which all the bits it has CNT is at least 2. And now we have to clear CNT. And we will do it like that. And so the complexity is the size of input. In problem C, we are given numbers n and x. We want to find minimal m such that end of all the numbers from n to m is equal to x. Well, that sounds stupid. First of all, it should be pretty easy to just calculate this value. We need to understand, is it true that like for each bit, is it true that all the numbers on the segment have this bit? That sounds very easy. Like for example, if we want to do it for case bit, we know that if there are at least 2 to the power of k plus 1 numbers on our segment, then in at least one of them this bit will be 0. Otherwise we just check that both n and m have this bit, and thus if at least one of them don't, then obviously the end is 0 in this bit. Otherwise, it's impossible that we start with 1, then move to 0, then eat up the whole segment of zeros, because it has length 2 to the power of k, and we know that the length of this segment is smaller than that. So yeah, we can calculate this thing in of number of bits, and actually even like log of number of bits, or maybe even like using some built-in functions, probably even in constant time. Like, what do we need? We need to take end of n and m, that's constant time, and then we have to zero out some bits for which the length of the segment is bigger than 2 to the power of k, but that's just some suffix of bits. And to find the length of this suffix, we need to understand what is the largest power of 2 that is at most m minus n, and that sounds like taking the highest one bit in m minus n. So there is a built-in function for that. I don't know if it works in constant time, but I think it does. Yeah, so after that, yeah, when we increase m, this thing can only decrease, like it's not non-increasing, because we add some numbers to end, so it will it can only go down. So we can apply binary search on m, and so we do binary search. We can just calculate this in constant time, and we will find where we can get x, if we even can. Yeah. But also it seems like this should be solvable even without binary search. Like basically we start with n, then we end it with some numbers that can like turn off some bits that were 1 in n. It can make them 0. So x should be a submask of n, and to get x we need to flip some of the bits. So we need to get in this end some number that have 0 in given bit. So we're looking at bits that are set in n but not set in x, and for each of them we should reach at least one number that has 0 in that bit. But that like should be the closest to n on the right number that have 0 in this bit, and that should be pretty simple. Like we know that n has 1 in that bit, so when we increase it the first time it get 0, like it will be all zeros to the end. So we like look at the higher bits to that one, add 1 to that, and then write down zeros. Okay, so when we do that for the highest bit for which we should do that next, we also will do it for all the smaller bits. So we only need to do it for the highest bit, and then either the number we get is the answer or it's impossible to get x. So this is a solution in constant time. So let's go through this one more time. X should be a submask of n. If it's not true, then there is no answer. If n is equal to x, we can just take one number, so n is the answer in that case. We can write, yeah, for 10 tens, the answer is 10. And now we will look at number that have only bits that are 1 in n but 0 in x, and that is n XOR x, because we know that x is a submask of n. Normally we should do something like that, but we know that x and n is x. So this is our number. Okay, now now we want to understand what is the largest bit of that number, and that is 63 minus the number of leading zeros. I think it's like that, but it should be right. If we have like this built-in function calculates the number of leading zeros in the number, interpreting it as unsigned long. If it has no leading zeros, then the highest bit is 63. So okay, so this is the highest bit. We know that in n this bit is 1. Let's insert it. We can also like check that we actually correctly calculated this. What is the property that this bit is the highest one? Well, x is at least 2 to the power of this number, but it should be strictly smaller than 2 to the power of next bit. So k plus 1. And should have this bit. So how does m look? Well, we ignore k smaller bits, then increase everything else by 1, and then add k zeros in the end. So that's our m. And we can show that the end on segment from n to m is actually equal to just end of n and m, similarly to how we showed how to calculate m. So if their end is equal to x, then m is the answer. Otherwise, there is no answer. Yeah, I guess I used this incorrectly. Let's think again. This should be, oh, it should be y here, not x. Okay, this looks like correct answer. So a bit of bit magic, huh? And we get solution in constant time, which is cool. Cannot do better than that. So let's move on to problem D. Yet another problem about graph on non-k-prime numbers. So it looks like we will have n numbers and then we build the graph. Yeah, I'm living near the airport. Sorry about that. So we have n numbers. We build a graph on n vertices. Two vertices are connected if their numbers are not co-prime, so their GCD is not 1. So like there is some k that both of those numbers are divisible by k. Okay, so we build this graph. Looks like this, I guess. And we literally asked to write BFS in this graph. Who is the coordinator of this contest? There are a lot of problems about the graphs, and like no sane person would think that this problem had never appeared. Okay, this is so bad. Like I would understand if there is like queries, but also I am sure that if it's solvable, it also appeared before. Not sure if it's solvable. Probably not, but yeah, this is just crazy. Well, okay. When you're having a problem about these graphs with prime numbers, the thing you do is like, what's the issue? Why we can't just run BFS? We can just run BFS because the graph is given in indirect way, and so it can have n squared edges, or maybe even if it doesn't, we don't know how to like find all the edges. So what you want to do in such situations, well, in general, when you're given in an indirect given graph, you want to usually you want to build an explicitly built graph with some not very big number of vertices and edges that have the same properties like in the things you're interested in. Like here we're interested in distances. Maybe you're interested in like connected components or something like I don't know, minimum spanning tree, something. Like if you can build a graph that has the same answer as the graph in question, and it is explicitly given, then you can just run a standard algorithm on that graph. And so we want to try to do that here. So we want to build a graph that preserves distances, or like maybe distort distances in some predictable way. Then we will run BFS on that graph, and that's it. So how do we build an auxiliary graph in this case? Well, when you are working with this graph, like edges mean k prime, not k prime. Usually, the idea is to add special vertices corresponding to prime divisors, like just prime numbers. We know that all our numbers are up to this, so all the prime divisors are also up to this, so we just add all the prime numbers that are up to this number. And like, how do we explain that there is an edge between these two vertices? Well, they should have a common prime divisor. So how can we simulate it using our prime numbers? Well, we can draw an edge between this like each vertex and all its prime divisors. Then if two vertices had a common prime divisor, then both of them will be connected to the same prime number. So if there was a direct edge, there will be like a path of length 2. If they were not connected, then they won't have any common prime divisors, so they won't have a path of length 2. And we can see that like the graph we built is bipartite. So when we are moving, we will alternate between parts. So each path from one initial vertex to another initial vertex will look like we start here, then we move to some its prime divisor, then we move to some other number that also has prime divisor. That means that like in the initial graph we just move in using this edge. So in this new graph we'll just run BFS, find the shortest path, and just print the vertices that are initially present. Why does this graph have a small number of vertices and edges? Well, vertices is just n plus the number of prime numbers up to this. And edges, for each of the initial vertices, its degree is just the number of different prime divisors it has, and that is obviously bounded by log c. So the number of edges is bounded by n log c, and it is actually smaller than that. I think that the number of different prime divisors should be like O of log c divided by log c. But that doesn't matter. And n log c is fine too. Yeah, and that's it. We don't even we have to build the graph explicitly because we have to know the edges like from the prime numbers back. We can iterate over all the edges from the number to its prime divisors using sieve just in log c time, but we also need edges in the other direction, and like we need to find them explicitly in store. 2 seconds, like that's a lot of pushbacks, which is not very nice, but well, that's surely the way to go. So it's not like we can do something about it. Like we can eliminate vectors. Okay, yeah. Let's try to write this without vectors. So, how will that work? How did I do that? Increased. Yeah. So we will need an Ertas finis sieve, which for each number stores its smallest prime divisor, and we will actually use like the ID of its smallest prime divisor. So in our graph there will be n plus the number of primes up to n numbers, that is at most to n, so the size of the queue, dist array, and parents will start to restore the path will be all up to 2 times n. now like the biggest issue, how do we store all the edges from primes to the vertices? We'll just store them in one array. And to do that, we will first calculate the degree for each prime. Then we will calculate prefix sums on this thing. Like this is kind of like count sort, right? We need to well, basically we want to group the edges by its starting point, so it's basically counting sort. Okay, we count how much space do we need, then we count prefix sums that will mean like the boundaries between different vertices in this array. And then we will run through it one more time and actually fill up this array. And then when we want to iterate all the neighbors of the given prime number, we know the segment in this array that we should look through, and yeah, we just iterate it. Okay, so let's start with finding, calculating the sieve. So in array D, we will store the index of the smallest prime divisor. If number x already have a prime divisor, then it is not prime itself. Otherwise, we iterate over all the numbers that are divisible by x, and if they do not have their smallest prime divisor, then their smallest prime divisor is x. And we have found another prime number. So I'm counting prime numbers, so when we encounter new one, its index is m, and then we do m++. So that works as sieve in n log n time. Okay, so now we read the array and we want to find all the edges. To do that, we will okay, I need to actually store the prime numbers because I need to divide by them. Okay. So this is the array of prime numbers by index, and so I'm saying that the m's prime number is x. So while I'm greater than 1, so I have some prime divisors, I will take the smallest of them, which is stored here, and then while I'm divisible by this number to 0, I will divide myself by this number, so I remove all the occurrences of this prime divisor, and I want to add edge between like initial x and prime y. I will number the vertices in my graph, like from 0 to n it will be initial vertices, and from n to n plus m the prime numbers. So I want to say that right now the degree of corresponding to this prime number is increased by 1. I will return to this place because we will need to change it a bit. Okay, so now all the decks are calculated, and now I want to calculate the prefix sums. The problem with this approach is that I want to have 0 as, like, I want to have boundaries for all the segments in this array now. Like the first boundary is 0, but deck of 0 is the number of edges it has, so it's like the second boundary we want. So instead of doing this, we will do +1 here. So now like the array is shifted by 1, and so when we calculate prefix sums, it will be exactly boundaries. And that means that for each number, we now store the start of its array in Jack for its ID. Now we do this thing again, except we don't read the number. And here we want to actually add the edge. So in G of the position we want, we will put I, that's where the edge goes, and I want to say that we should this now stands for the next position in the list, so I want to increase it by 1. Like I already filled this position, so the next one I should fill should be greater by 1. And now I have messed up this array. I still want it to be the boundaries. And how to do that? Well, actually, how did I mess up? For each vertex, I move it from the start of its segment to the end. But the end of this segment is the start of the next segment. So if I move everything by 1 to the right, and then put 0 where it belongs, I get what I want. Like instead of doing this +1, I could have put this thing here after calculation prefix sums. Okay, so now we just run BFS. Have start and finish. So we have two types of vertices, and we will iterate over their edges differently depending on their type. So the type is defined by whether it is smaller than n or not. If it is smaller than n, then it is the number. And to iterate over its neighbors, we want to use this. Okay, we have an edge to y, which is actually has id n plus y in the graph. So if its dist is greater than dist plus 1, then we store the dist, we put the par, and we put it into the queue. Otherwise, we just iterating over all the things we wanted to iterate over. Like we know that the edges for vertex v are stored in the array G. Like we put them here from this point to this point. So we just iterating over them. G of J and this. So that's our BFS. If dist is big, then it's not reachable. Otherwise, so we are staying in T, and while we haven't reached S, we go to the parent, but that will move us to the prime we want to use. So we take parent again, and that will take us to the next number we want. Interesting. Okay. It can die in this while. Or it can die in some other while. Let's find out. Okay, so it dies somewhere here. minus 1. Great. Oh, should be this one here. Okay. Can I move myself? Oh, cool. I can move myself. And so. I was kind of greedy with the arrays. Like, the right thing to do here is just say that. Like, I could forgot to put 2n in some array. No, I think it should be fine. Okay, problem E. What a great story. I just love this. So we have sequence of numbers, can perform some operations. In each operation we choose subsequence, and then first number is northern in this subsequence, and then they alternate, like northern, southern, northern, southern. After that you can do one of the following: add 1 to all northern, subtract 1 from all south, or vice versa. Okay. Note that operations are independent. The numbers are no longer called northern or southern when operation ends. You want to turn all the numbers into zeros. There is very little time left. What is the minimum number of operations? Okay, so we have an array of numbers. We want to make all of them zeros, applying the minimum number of operations. In each operation we choose some subsequence and then do +1 -1 +1 alternatingly on the subsequence, and we can choose if we want to do +1 or -1 in the beginning. Okay, so we cannot change sum much by each operation. Like if we choose even number of numbers and the sum doesn't change, otherwise it will be either increased or decreased by 1. So we have to spend at least absolute value of some operations, but it might be not enough. doesn't sound very simple. Oh yeah, we can also say the following. If we look at some segment of initial array, the sum on this segment also either is not changed by each operation or like increased by 1 or decreased by 1. So the answer is bounded by maximum of absolute values of sums on subsegment. And it feels like that's the answer. Like, I'm not sure why, but it feels like it's optimal. Like, okay, why is that? Why that can be true? Let's look at the prefix sums, right? So, our value is the maximum difference between two prefix sums. And I want to say that in one operation I can surely decrease that. How to do that? Well, if it's 0, then we are done. Otherwise, what is the maximum difference? Well, we should take maximum prefix sum, minimum prefix sum. So I want to, for example, decrease all maximum prefix sums by 1, but not decrease minimum prefix sums by 1. And that sounds doable if the first maximum prefix sum is before the first minimum. Like, if the first maximum prefix sum is before the first minimum, then I will do -1 before first maximum prefix sum, and then do +1 before the first minimum prefix sum. So I decrease all prefix sums between them, and then like I can do the same to the right. Yeah, and if it's vice versa, then we will increase minimum prefix sums and not increase maximum prefix sums. So we just calculate prefix sums, and the answer is maximum prefix sum minus minimum prefix sum. Cool problem. Like, well, you can see how I approached it. Like, I found some lower bound, then I found a better lower bound. Like, how did I do that? Well, I thought like, yeah, absolute value of sum is lower bound for sure, but like we can have an array like 5 minus 5, and obviously we have to spend at least 5 operations, even though the sum is 0. But then I thought, well, okay, what if my array is like 5, 5, 5, minus 5, minus 5, minus 5? I cannot decrease all the 5s on the prefix at the same time. So maybe like I look them as one unit, and then I get like this better lower bound, and it feels like it should be possible to spend that number of operations. So then I try to prove it. Like I look at how do I calculate this lower bound, and how can I make sure that it decreases with each operation. So I know that this thing cannot decrease by more than 1, and if I decrease it by 1 every time, then I will be successful. Nice problem. And the last problem, problem F. We have some rectangular grid. N of the squares are occupied by a lab block, whatever that is. Each block has 4 walls. If a wall is between 2 occupied squares, it is an inside wall, otherwise it is outside wall. Outside walls must be insulated. So we want for the number of outside walls will be insulated okay, so we are interested in ways to make a figure of exactly n squares on the grid such that it minimizes the number of outside walls, the perimeter of the figure, and we have 2 types of tests. Either we want to actually print it, I guess, like this, or we want to calculate the number of ways to construct this thing modulo some given prime. And like all of our ends are bounded by something, but we have multi-test, and only if we have to print the answer then the sum of n is bounded, otherwise the sum of n is not bounded. Okay, that reminds me about a problem from Timus, but it's much simpler than that. The problem from Timus I haven't actually solved. So, okay, let's look at horizontal walls. Let's look at a column in which we will have at least one square chosen. Then it has a lower side and an upper side. So for each such column we will have at least two walls. So the answer is bounded by the number of columns we use plus the number of rows we use for the same reasons, multiplied by 2. And it is achievable. Like if we fix the number of rows we use as x and then the number of columns we use as y, then we can just fill in the rectangle and spend x times y blocks. If it is smaller than that, it's just impossible. We put all the blocks that we can put using only these rows and these columns. But if it is bigger than n, we can start to remove blocks one by one, starting from the corner, and this will not change the perimeter, and so it is minimum possible. Okay, so yeah, we need to choose how do we split, how do we choose x and y. So we want to choose x and y such that their product is at least n and their sum is minimal. Well, that means that x and y should be as equal as possible. So either they're equal or they differ by 1. Because otherwise we can increase the smaller number by 1 and decrease the bigger number by 1. That will like the sum will stay the same, but the product will decrease. Product will increase. Sorry. So just printing one way is very easy. How to calculate the number of ways? I guess I finally have to draw something. So I have my n, and I can find the minimum possible perimeter. And we know that like it is bounded by 4 times square root of n rounded up, right? Like if x and y are both square root of n rounded up, then their product is at least n, obviously, so the answer should be at most this. That means that we can just try all the ways to choose x and y with given sum, check that their product is at least n, and well, I guess that there shouldn't be like a lot of them. Like we know that there will be at most square root n of them, but probably it is even smaller than that. Because like if we say that x is even like square root of n rounded up plus d, and then y should be at most this, maybe even smaller, then their product is square root of n rounded up square minus d square. This is like it should be bounded by something like, I mean, okay, this is strictly smaller than square root of n plus 1. So we take square of that, we will get n plus 2 square root of n plus 1. And so if d square is greater than this, then the product is smaller than n, and it is not viable. So d is actually like fourth root of n order of magnitude. So yeah, we can try all the options. There will be a small number of them. Okay, so now we have fixed a rectangle, and we want to choose exactly n of its cells, and we know something. Like, we know that we cannot cut the whole column. So like the number of cells here is x times y, and we know that it is strictly smaller than n times y. Let's say that y is at most x. Strictly smaller. And this means that y is at most square root of n rounded up. Okay. We want the perimeter of our figure to be equal to the perimeter of this rectangle, and as we proved it, like that means that for each column and each row, it should only have like one left border and one right border. So this figure should be like kind of convex, in the sense that it should not have like rows with empty space between, because that would increase the perimeter. Okay, that means that we should like cut some parts of every angle, and it should be like more with each row. Like we cannot cut something like that, because this would be this would be a column with an empty space between. Why those corners cannot intersect? Well, that would mean that we can drop this whole column, and we know that it is not possible. So the corners are independent, and what's better is that we don't actually care about the dimensions of the rectangle when we solve for one corner, because well, we know that we won't reach this corner and this corner, so we can just imagine that it's like infinite in that direction and we are just cutting something. So what do we want to know? We want to calculate the number of ways to cut some fixed number of blocks, and that number of blocks is bounded by square root of n. Okay, that sounds like a DP problem, right? So what are we interested in? Okay. We don't care how many rows we cut here, but we do care that rows should like either increase or decrease, but it shouldn't matter, right? Like so we will have like dp the number of ways to cut m cells if in the last row we cut k cells, and then we try all the numbers for the next row, either up to k or vice versa, like from k up. And we know that both of those things are bounded by square root of n. So even the stupid implementation of that will be like square root of n, and square root of n transitions, which is fine. But also we can optimize it with prefix sums. Like, for example, if we will increase k, then for fixed transition, we want to have a sum of these dp values over all smaller k. Yeah, and then after we calculate this dp, we just sum it up over k, so we know how many ways are there to cut m blocks in one corner, but then we have 4 corners. So we basically multiply for polynomials, like calculate the first power of this polynomial. But since it has square root length, we don't need any like FT or something, just multiply in square time and it will be linear. So yeah, and this is all pre-calculation. Like we calculate it once for given modulo, and then to answer the query we will find the smallest perimeter and then try all the ways to like choose the dimensions of the rectangle. And for given dimensions of the rectangle, we know what should be the total size of the corners we cut, and we just look at the pre-calculated value and add it to answer. No two of our constructions can be the same because they have different bounding boxes, different dimensions of bounding boxes. So that's it. Again, non-constant module. What do I need? I think I can do the first type of query construction just on the fly. So okay, so first we read the number of tests and the type. If type is 1, then this means find the squarest rectangle that has area at least n, and now just print it. What do I have to print? The dimensions, and then so the dimensions x by y, and then I know that I will have each row almost completely filled, and for first n minus x times y minus 1 rows, I need to fill it completely, otherwise not. That's it. Okay, so now we are reading the modular. Then do precalc, and then just easily answer each query. So first I want to find the perimeter. Let's say that I will do that in log time. So I can do binary search on the sum, and for a fixed sum, like the squarest possible figure is x over 2 rounded up times x over 2 rounded down, and so if it is enough, then it's okay, otherwise it's not okay. So R is our sum, And now we will iterate over all the rectangles that have sum of sides equal to r and the product of sides at least n. And now we take pre-calculated answer for the case when we need to remove these many blocks from our rectangle, from all four corners. But also here I'm considering only rectangles in which x is the smaller side. X can be also the bigger side, so if x is not equal to r minus x, I can flip it and I should add the same thing to the answer again. And that's it. Okay, and now pre-calc. So dp of number of blocks I took and the last row, iterating over the number of blocks in increasing order, iterating over the last block I took, and just saying that this thing is equal to prefix sums for what? I had s minus x blocks removed before that, and my last row should be at most x, so the prefix sums is stored in x plus 1. And then I should calculate the prefix sums. Okay, now I need to so this dp is calculated for corner. Now I calculate the number of ways to remove exactly s blocks from each corner. That's just sum it up over the second dimension. And now I have to calculate the first power of this polynomial, and that is done by calculating its square twice. That's it. That's the minimum perimeter. Yeah, I can do that. That's 2 times the sum. Cool. Well, yeah, that was pretty easy contest. Problems. Oh yeah, the problem E is pretty nice. Problem D is an abomination. I mean, the concept is nice, but this shouldn't be used as a problem in a contest. F is also like so in terms of freshness. Like constructing is surely known. Calculating, I think it's also known. Okay. Thanks for watching. Bye.